Okay, so let's dive in. We're tackling Bayesian statistics today.
Yeah.
And trust me, it's going to be a lot more fun than it sounds.
Mm-hmm.
Our source material is this book, Bayesian Statistics, The Fun Way,
Yeah.
by Will Kurt.
Uh-huh.
And he's a beta scientist who seems to have, cracked the code on making this stuff engaging.
He really does. Yeah, he has a knack for making complex ideas approachable.
Yeah, exactly. From Star Wars to
Uh,
Legos,
Yeah.
he uses examples that just feel surprisingly relevant.
Yeah.
So our mission for this deep dive
Oh,
is to distill the essence of Bayesian thinking, see how it helps us make decisions in uncertain situations, and basically give you a new lens for understanding probability in your everyday life.
Yeah.
What do you think?
Yeah. Sounds like a plan.
Right. So before we jump into the book itself,
Okay.
I'm curious about Will Kurt.
Yeah.
Who is this guy? What's his background?
Well, he's not exactly a celebrity, but in the data science world, he's making waves. He's currently a data scientist at Wayfair, where he's been applying Bayesian statistics to real-world business problems for years. But what's fascinating is his passion for making this stuff accessible to everyone.
I noticed that. He runs a blog about probability, countbasie.com.
Yeah.
And he even wrote a book on functional programming with Haskell.
Uh-huh.
Clearly, this guy loves teaching.
Absolutely. And that teaching background really shines through in Bayesian statistics the fun way.
Yeah.
He takes something that can feel very academic and makes it feel like you're chatting with a friend at a coffee shop, not slogging through a textbook.
Okay. So now that we have a sense of who Will Kurt is,
Yeah.
let's get into the book itself.
Okay.
What's the big idea he's trying to convey?
The central thesis is that Bayesian statistics is more than just formulas and equations.
Okay.
It's a fundamentally different way of thinking about the world, especially when we're dealing with uncertainty.
Yeah.
Kurt argues that we can use this kind of reasoning to make better decisions, whether we're assessing risks, analyzing data, or just trying to figure out if that email promising $1 million is legit.
Yeah. It's like a mental upgrade for dealing with the unknown.
Exactly. And he emphasizes that Bayesian thinking helps us refine our beliefs as we gather new information, which is incredibly valuable in a world overflowing with data.
Okay. So Kurt's on a mission to make us all better thinkers.
Yeah.
How does he actually structure the book?
He divides it into several parts, each focusing on a different aspect of Bayesian thinking.
Okay.
He starts with the fundamentals of probability, laying the groundwork for understanding how Bayes' theorem works in practice.
Got it. So he's building a foundation before he gets to the really cool stuff.
Right. He introduces core concepts like probability distributions, which help us visualize uncertainty,
Yeah.
and conditional probability, which explores how probabilities change when we learn new information.
And I bet he uses those fun, relatable examples to explain these ideas.
You bet. From UFO sightings
Yep.
to zombie apocalypses, he finds ways to make even the most abstract concepts relatable and engaging.
Zombies.
Yeah.
Now that's my kind of math.
Right.
So after he covers the basics, where does he go from there?
He delves deeper into Bayesian probability itself, explaining how to use Bayes' theorem to update our beliefs as we get new evidence.
Okay.
For example, he talks about how seeing a string of sunny days might change our belief about the chance of rain tomorrow.
So it's like we're constantly refining our understanding of the world as we gather more data.
Exactly.
Yeah.
And that's a powerful concept with applications far beyond statistics.
Okay, so we've got probability, Bayesian thinking, and evidence.
Yeah.
What else does Kurt explore?
Well, he gets into parameter estimation,
Yeah.
which is basically figuring out unknown values based on the data we have.
Okay.
Like, if you see 10 birds and 7 are red,
Right.
how can you estimate the true percentage of red birds in the entire population? It's like being a statistical detective.
I like it. So he's giving us the tools to become data sleuths.
Precisely. And he introduces techniques like using the spread of our data to understand uncertainty
Okay.
and working with probability distributions to refine our estimates.
Okay, so we've got the basics, Bayesian thinking, parameter estimation. What's the final piece of the puzzle?
The final part of the book focuses on hypothesis testing,
Okay.
which is the heart of statistical decision-making. He walks us through how to use Bayesian methods to compare different hypotheses
Okay.
and see which one best fits the evidence we have.
Yeah.
It's like a statistical showdown
Oh, I like it.
between competing theories.
So if we have two possible explanations for something,
Yeah.
Bayesian analysis can help us figure out which one is more likely to be true.
Exactly.
Okay.
He uses real-world examples to illustrate this,
Yeah.
like the classic Monty Hall problem,
Eh.
and even an episode of The Twilight Zone.
Oh, wow.
He's really pulling out all the stops to make this as engaging as possible.
Okay, I'm officially hooked. So we have a good overview of the book's structure
Uh-huh.
and the main concepts it covers. Now let's dive into some of the chapters and
Ah,
see what nuggets of wisdom we can extract.
sounds good to me.
Where should we start?
Well, chapter 1 is titled Bayesian Thinking and Everyday Reasoning.
Okay.
Yeah.
I'm curious to see how he connects this seemingly complex concept to our everyday lives.
That's a great place to start.
Yeah.
He jumps right in by showing us how we already use Bayesian-like thinking all the time, even if we don't realize it.
Okay.
For example, he uses the classic scenario of seeing bright lights outside your window
Right.
and wondering if it's a UFO.
Ah, the age-old question.
Right. And he points out that our brains instinctively try to make sense of uncertain situations like this
Yeah.
by generating hypotheses and evaluating evidence.
So we see something unusual and our minds start playing detective,
Yeah.
trying to figure out what's going on.
Exactly.
Hmm.
And Kurt argues that this is essentially what Bayesian statistics is all about. Using evidence to update our beliefs about the world.
Okay, so let's break this down.
Yeah.
What are the key points he makes in this chapter to
Okay.
introduce these ideas?
Well, he starts by emphasizing that probability isn't just some abstract concept.
Mm-hmm.
It's a way of quantifying our uncertainty about the world.
Okay.
We might say things like,
Yeah.
it's likely to rain, or I
Yeah.
doubt I'll win the lottery.
Uh,
But probability gives us a more precise way to express those beliefs.
so instead of just vague feelings, we can assign numbers to those probabilities,
Right,
like
well-
saying there's a 70% chance of rain or a 1 in 10 million chance of winning the lottery.
Exactly. And this numerical representation is crucial for applying Bayes' theorem. Then he dives into Bayesian thinking itself,
Okay.
which he describes as a continuous process of updating our beliefs as we encounter new evidence.
So it's not a one-and-done calculation.
Right.
It's a dynamic process of constantly refining our understanding.
Precisely. And Bayes' theorem provides the mathematical framework for doing this, showing us how to combine our prior beliefs
Okay.
with new evidence to arrive at a revised or posterior belief.
Okay, I'm starting to get a sense of the flow here.
Yeah.
We start with a belief, we encounter new evidence,
Right.
and then we use Bayes' theorem to update our belief accordingly.
That's a great summary. And to make this more concrete, he uses the example of trying to figure out if someone is lying.
Ooh, that's a good one. So let's say our friend tells us they aced their exam.
Right. Our initial belief might be that they're telling the truth,
Yeah.
especially if we generally trust this friend.
But then let's say we find out they have a history of embellishing their accomplishments.
Right.
That's our new evidence.
Exactly. And using Bayes' theorem, we can combine that new information with our initial belief
Yeah.
to update our assessment of whether they're being truthful this time.
So our updated belief might be that they're less likely to be telling the truth
Right.
than we initially thought, given their track record.
Precisely. And that's a real-world example of Bayesian thinking in action.
Yeah.
We start with a belief,
Mm-hmm.
encounter new information,
Right.
and adjust our belief accordingly.
Okay, I like how he's bringing it down to earth with examples like this.
Yeah.
It makes Bayesian thinking feel much more applicable to everyday life.
Absolutely. And that's the beauty of this book. It takes something that can feel intimidating and makes it relevant.
Yeah.
And even fun.
So Chapter 1 lays the groundwork, introducing probability, Bayesian thinking,
Uh-huh.
and Bayes' theorem itself.
Right.
Where do we go from here?
Chapter 2, Measuring Uncertainty,
Okay.
is where Kurt dives into the nuts and bolts of assigning numerical values to our beliefs.
Okay.
We're going beyond vague terms like likely and unlikely
Mhm.
and learning how to express our uncertainty with more precision.
So instead of just saying, I think it might rain,
Right.
but we could actually say
Yeah.
there's a 60% chance of rain.
Exactly. And this precision is crucial for using Bayes' theorem effectively.
Okay, so how does he approach this idea of measuring uncertainty?
He starts by revisiting the concept of probability as a scale from 0 to 1.
Okay.
0 represents absolute certainty that something is false,
Uh-huh.
while 1 represents absolute certainty that it's true.
So if I'm absolutely sure the sun will rise tomorrow,
Yeah,
that would have a probability of 1.
precisely. And if you're certain you won't win the lottery, that would have a probability of 0.
Right. But most things in life fall somewhere in between those extremes.
Exactly. And that's where things get interesting.
Okay.
Kurt explains how we can assign probabilities to events that are uncertain
Yeah.
based on our best judgment and the information we have available.
So if I say, I'm pretty sure it will rain tomorrow, but I'm not totally certain, I might give that a probability of, say, 0.8.
Exactly. And that's where subjective judgment comes into play.
Okay.
Different people might assign different probabilities to the same event based on their own experiences and perspectives.
So a meteorologist might assign a different probability to rain than someone who just looks out the window.
That's right. And this is one of the things that makes Bayesian statistics unique.
Yeah.
It acknowledges that our beliefs and perspectives matter and that they can influence how we interpret data.
So it's not just about crunching numbers.
Right.
It's about understanding the context and the perspectives involved.
Exactly. And this makes it particularly useful for dealing with real-world problems where we often have incomplete information and need to factor in different viewpoints.
Okay, so we've got probability on a scale of 0 to 1.
Yeah.
And we've talked about how personal judgment can factor in. What else does Kurt cover in this chapter?
He introduces the concept of probability distributions, which are basically visual representations of our uncertainty. Instead of just giving a single number for probability, we can represent a range of possibilities and how likely each one is.
So it's like seeing the full spectrum of what could happen.
Precisely.
Not just the single best guess.
He uses a classic example.
Okay.
Flipping a coin 6 times. Instead of just saying the chance of heads is 50%, we can show the probability of getting 0 heads, 1 head, 2 heads, all the way up to 6 heads, giving us a richer picture of the possible outcomes.
Okay, so instead of just one data point, we're seeing a whole distribution of possibilities, which seems a lot more realistic for most situations.
Exactly. And that's why probability distributions are such powerful tools for understanding and dealing with uncertainty.
Okay. Chapter 2 is all about quantifying uncertainty from the 0 to 1 scale to subjective judgment and those visual probability distributions. What comes next?
In Chapter 3, The Logic of Uncertainty, Kurt dives into how we can use logic to combine and manipulate probabilities. It's like we're learning the rules of the game, how probabilities interact with each other.
So instead of just dealing with individual probabilities, we're starting to connect them and build more complex scenarios.
And this is where the real power of Bayesian reasoning starts to shine.
Okay, I'm ready to level up my probabilistic thinking.
Good.
What kind of logical operations does he introduce?
He focuses on the familiar concepts of and, or, and not, the building blocks of logic. They might seem basic, but they're incredibly powerful when applied to probabilities.
So it's like taking what we know about logic and applying it to the world of uncertainty.
Precisely. With and, we figure out the probability of 2 events happening together. For example, the probability of rolling a 6 on a die and flipping heads on a coin. Kurt shows us how to calculate these combined probabilities using the product rule.
So we multiply the probability of each individual event to get the probability of both happening.
That's right. And then with OR, we're looking at the probability of at least one of 2 events happening. Like rolling a 6 on a die or flipping heads on a coin. Kurt explains that this calculation is a bit trickier because we need to consider whether the events can happen at the same time or not.
Right. Like rolling a 6 and rolling a 5 can't both happen with one roll. But flipping heads and rolling a 6 can happen simultaneously. Those are called mutually exclusive events,
Exactly. And Kurt walks us through the formulas for calculating or probabilities in both cases, using clear examples to illustrate the differences.
So and D is about both events happening, and or is about at least one of them happening. What about not?
Not is all about calculating the probability of something not happening. So if the probability of rain tomorrow is 60%, the probability of it not raining is 40%. It's like flipping the coin to the other side.
I see. It's like we're building a set of rules for how probabilities work together.
Precisely. And these rules are essential for understanding the more complex calculations we'll encounter later on.
So Chapter 3 is all about using logic to manipulate probabilities. What's the big takeaway here?
The key takeaway is that logic isn't just for philosophers and computer scientists. It's a fundamental tool for reasoning about uncertainty. By applying these logical operators to probabilities,
Uh-huh.
we can build more sophisticated models of how the world works.
It's like we're taking these simple building blocks of logic and using them to construct complex probabilistic structures.
Exactly. And this logical framework is essential for understanding how Bayes' theorem works
Yeah.
and how we can use it to refine our beliefs as we encounter new information.
Okay. I'm starting to see how all these pieces fit together. Where does Kurt go from here?
In Chapter 4, creating a binomial probability distribution,
Okay.
we take another step deeper into the world of probability distributions.
Okay.
We move beyond single probabilities
Yeah.
and explore how probabilities are distributed across a range of possibilities.
Okay. So instead of just asking, will I win the lottery?
Mm-hmm.
We might ask,
Yeah.
what are the chances of winning different amounts of money?
Exactly. And probability distributions give us the tools to answer questions like that.
Okay.
This chapter focuses on the binomial probability distribution,
Uh-huh.
which is particularly useful when dealing with situations where we have a set number of trials,
Okay.
each with two possible outcomes.
Can you give an example of what you mean?
Sure. Kurt uses the example of flipping a coin 10 times
Okay.
and counting how many times it lands on heads.
Uh-huh.
Each coin flip is a trial,
Okay.
with heads or tails as the two possible outcomes.
Right. So the binomial distribution could tell us the probability of getting 0 heads. 1 head, 2 heads, all the way up to 10 heads.
Exactly. And it's surprisingly applicable to many real-world scenarios.
Yeah.
Imagine analyzing the success rates of marketing campaigns.
Okay.
Each potential customer is like a coin flip. They either convert or they don't.
Okay, that makes sense.
Yeah.
So how do we actually create one of these binomial probability distributions?
It involves some math, of course,
Mhm.
but Kurt breaks down the formula in a way that's easy to follow.
Okay.
He explains that the formula takes into account the number of trials,
Yeah.
the probability of success on each trial,
Mhm.
and the specific number of successes we're interested in.
So it's like a recipe with specific ingredients that allows us to calculate those probability.
Precisely. And he provides clear examples and exercises to help readers get a handle on the formula.
Okay, so we're learning how to create a binomial distribution.
Yeah.
What's the key takeaway from Chapter 4?
The key takeaway is that probability distributions are incredibly powerful tools for analyzing situations with multiple possible outcomes.
Okay.
And the binomial distribution in particular is incredibly versatile, applicable to everything from coin flips
Yeah.
to marketing campaigns
Right,
to
right.
medical trials.
It's like adding a whole new weapon to our statistical arsenal.
Absolutely. And we'll continue to explore different types of probability distributions and their applications as we move through the book.
Fantastic. Now on to Chapter 5.
Chapter 5, the beta distribution, introduces us to our first continuous probability distribution,
Okay.
which opens up a whole new realm of possibilities.
Continuous. What does that mean in this context?
It means that the variable we're modeling can take on any value within a given range,
Okay.
not just discrete values like the number of heads in a coin flip.
So instead of just dealing with whole numbers,
Mm-hmm.
we're dealing with decimals and fractions,
Right.
representing a more continuous range of outcomes?
Exactly.
Okay.
And the beta distribution specifically is incredibly useful for modeling probabilities themselves.
So it's like a probability distribution of probabilities.
Yeah.
That sounds a little meta.
It is a bit meta, but it's a really powerful concept.
Okay.
Imagine you have a mysterious coin dispensing machine
Right.
that sometimes gives you 2 quarters when you put one in, and sometimes just keeps your money.
Okay, that sounds both intriguing and potentially frustrating.
Right.
Yeah.
So you don't know the true probability of getting 2 quarters back,
Right.
but you can use the beta distribution to represent your uncertainty about that probability.
So I might start with a belief that the probability is somewhere between, say, 20% and 80%,
Huh.
but I'm not sure exactly where it falls.
Exactly. And the beta distribution allows you to capture that range of uncertainty.
Okay.
Then, as you use the machine and collect more data,
Yeah.
you can update your beta distribution to reflect your growing knowledge.
So if I get 2 quarters back 10 times in a row,
Yeah.
my beta distribution would shift to reflect a higher probability of success.
Precisely.
Okay.
And that dynamic updating is one of the most powerful features of the beta distribution.
Okay, so we've got this continuous probability distribution that models our uncertainty about probabilities themselves.
Yeah.
And it changes as we gather more data.
Right.
What's the key takeaway from Chapter 5?
The key takeaway is that the beta distribution is a flexible and powerful tool for working with probabilities, especially when we have limited information and need to incorporate our prior beliefs.
It's like a shape-shifting tool that helps us capture and refine our understanding of probabilities.
Exactly. And this flexibility makes it a key player in Bayesian statistics.
Fantastic.
Yeah.
Now, before we jump into the next chapter, let's pause for a moment and talk about the bigger picture.
Sounds good to me. What's on your mind?
We've covered the basics of probability,
Yeah.
logical operations,
Uh-huh.
and two types of probability distributions.
Yeah.
But why should our listener care about any of this?
That's a great question.
Yeah.
These concepts might seem abstract,
Mm.
but they have real-world applications in a ton of fields.
Oh.
We're talking finance, medicine, marketing, artificial intelligence. The list goes on.
So it's not just for math nerds.
Absolutely not. Anyone who deals with uncertainty and decision-making can benefit from understanding these concepts.
Can you give some concrete examples of how these ideas play out in different areas?
Sure. In finance, Bayesian methods are used to model market behavior and make investment decisions.
Mm-hmm.
In medicine, they help diagnose diseases
Okay.
and personalize treatment plans.
Yeah.
And in marketing, they're used to target advertising campaigns
Right.
and understand customer behavior.
So it's like a secret weapon for making smarter decisions in all areas of life.
That's a great way to put it.
Yeah.
By understanding probability, logic, and probability distributions, we can approach decision-making with more confidence and clarity,
Right.
regardless of our field.
Okay, you've convinced me. Now let's get back to Will Kurt and see what other gems he has in store for us.
Let's do it.
Chapter 6 is titled Conditional Probability, which sounds like we're getting to the heart of how Bayesian thinking works.
You're right. This is where we really start to see the mechanics of how we update our beliefs based on new information.
Okay.
Conditional probability is all about how the probability of one event changes when we know that another event has already occurred.
So it's like saying, if I know this,
Exactly.
what are the chances of that?
It's a crucial concept for understanding how evidence shapes our beliefs in the Bayesian world.
Hello?
To illustrate this,
Yeah.
Kurt uses a scenario that many people can relate to: online dating.
Okay, now that's a real-world example I can get behind.
Right. He talks about the conditional probability of finding a compatible partner,
Yeah.
given certain criteria,
Yeah.
like shared interests or location.
Okay.
He points out that as you learn more about a potential match,
Yeah.
the probability of compatibility might change,
Uh-huh.
either increasing or decreasing based on that new information.
So if you find out someone loves long walks on the beach and hates pineapple on pizza, just like you, the probability of compatibility might go up.
Exactly. It's all about how one piece of information can change the probability of another.
Yeah.
And that's how we constantly refine our understanding of the world,
Mm-hmm.
by updating our beliefs based on new evidence.
Okay, I'm starting to see how this works.
Yeah.
But why is this conditional probability idea so important for Bayesian thinking specifically?
It's important because it's the engine that drives the updating process in Bayesian statistics. Remember, we start with a prior belief, and then we use new information to modify that belief.
Right.
Conditional probability is the mathematical tool that allows us to make that modification.
So it's the bridge between our prior beliefs and our updated posterior beliefs.
Exactly.
Right.
And Kurt introduces a formula for calculating conditional probability,
Mm-hmm.
which shows us how to adjust our initial probability based on new information.
Okay, so we're getting into the mechanics of how it works.
Yeah.
What else does Kurt explore in this chapter?
Well, he also introduces the concept of independence,
Okay.
which is essentially the opposite of conditional probability.
So it's like saying, knowing this tells me nothing about that.
Precisely.
Okay.
Independent events are those where the outcome of one doesn't influence the probability of the other.
Yeah.
Like flipping a coin and rolling a die are independent events because what happens with the coin
Yeah.
doesn't affect what happens with the die.
Right. Knowing I flipped heads doesn't tell me anything about whether I'll roll a 6.
Exactly. And understanding independence is important because it simplifies our calculations and helps us to identify which pieces of information are truly relevant to our beliefs.
Okay, so we've got conditional probability, which tells us how probabilities change based on new info,
Yeah.
and independence, which is when events are unrelated. What's the key takeaway from Chapter 6?
The key takeaway is that conditional probability is a fundamental concept in Bayesian thinking. It's the mechanism that allows us to update our beliefs as we gather new evidence,
Right.
which is the essence of what makes Bayesian statistics so powerful and dynamic.
So it's like we're building a dynamic model of the world,
Exactly.
constantly adapting and refining our understanding as we learn more.
And this dynamic approach is what makes Bayesian statistics such a powerful tool for
Yeah.
navigating a world that's full of uncertainty and
Mm.
constant change.
Okay, I'm ready to keep building this model. What's next on our Bayesian journey?
Chapter 7 is where Kurt finally lays out the mathematical machinery of Bayes' theorem itself.
Okay.
He calls it Bayes' theorem, the math speaker. Chapter 8 dives deeper into those key ingredients of Bayes' theorem: the prior, the likelihood, and the posterior. It's like we're taking a closer look at each piece of the puzzle to see how they fit together.
Okay, so we're going beyond just plugging numbers into a formula.
Yeah.
And really understanding what each part represents.
Exactly. And Kurt starts by tackling one of the most debated aspects of Bayes' theorem, the prior probability.
I remember you mentioned that the prior can be a bit controversial. Why is that?
It's because the prior represents our initial beliefs,
Uh-huh.
which can be subjective. Some people find that unsettling. They argue that if different people can have different prior beliefs,
Right.
then Bayesian statistics becomes a matter of opinion,
Yeah.
not objective truth.
That's a fair point.
Yeah.
How does Kurt address this concern?
He acknowledges that prior beliefs can be subjective,
Mm-hmm.
but argues that they're unavoidable. We all come to any situation with pre-existing beliefs
Right.
based on our experiences,
Right.
knowledge, and intuition. Ignoring those beliefs would be unrealistic.
So it's not about pretending to be perfectly objective.
Right.
It's about acknowledging our starting point
Yeah,
and using it as a foundation for our analysis.
exactly. The key, Kurt emphasizes, is to be transparent about our prior beliefs
Mm-hmm.
and to choose them in a way that's reasonable and justifiable.
So if I'm trying to estimate the probability of rain tomorrow, I shouldn't just pull a number out of a hat.
Right.
I should consider things like the weather forecast,
Yeah.
historical data,
Mhm.
and my own observations to form a reasonable prior belief.
Precisely. And remember, the beauty of Bayesian statistics is that we can update our prior beliefs as we gather more evidence.
Right.
The prior is just the starting point. It's not set in stone.
Okay, so we've talked about the importance of prior probabilities and choosing them
Yeah.
thoughtfully. What about the likelihood?
The likelihood, as we discussed earlier, is all about connecting the evidence to the event we're interested in.
Right.
It tells us how probable the observed data is,
Yeah.
given that our hypothesis is true.
Right, so it's like asking, if this hypothesis is true,
Yeah.
how likely is it that we would see this particular evidence?
And Kurt explains how to calculate the likelihood in different situations,
Okay.
using clear examples to illustrate the process.
Can you give us an example of how he tackles the likelihood calculation?
Sure. He revisits that scenario of coming home to find your house potentially burglarized. Remember we had the evidence of the open door,
Yeah.
the broken windows,
Oh.
missing laptop?
And we were trying to decide between the robbery hypothesis
Right.
and the something else happened hypothesis.
Exactly. So to determine the likelihood, we need to consider how probable that evidence is under each hypothesis.
Okay.
If the robbery hypothesis is true,
Uh-huh.
it's quite likely we'd see that evidence.
Right. A burglar would likely force entry and steal valuables.
Exactly. But if the something else happened hypothesis is true,
Yeah.
it's less likely we'd see that exact combination of evidence.
Right.
It's possible,
Yeah.
but less probable.
So the likelihood calculation helps us weigh the evidence in favor of one hypothesis over another.
Precisely. And the strength of the evidence is reflected in the likelihood ratio. The higher the likelihood ratio, the
Wow.
more the evidence supports one hypothesis over the other.
Okay, so we've talked about prior probabilities and likelihoods. What about the posterior probability? What are the key takeaways there?
The posterior probability is the culmination of the Bayesian process. It's our updated belief about the probability of the event after considering the new evidence.
So it's like the final verdict,
Yeah.
our refined understanding of the situation.
Exactly. And Kurt emphasizes that the posterior probability isn't a single fixed value.
Okay.
It's a distribution of probabilities that reflects our remaining uncertainty.
Okay, so instead of getting one definitive answer, we get a range of possibilities and their associated probabilities.
Precisely. This distribution shows us the most likely outcome based on the data and our prior beliefs.
Mm-hmm.
But it also acknowledges that there's still some uncertainty involved.
So it's like a more nuanced and realistic view of the world,
Right.
acknowledging that we can't always know things with absolute certainty.
That's a great way to put it. And this nuanced understanding is one of the strengths of Bayesian statistics.
Yeah.
It forces us to grapple with uncertainty and to make decisions based on probabilities,
Right.
not absolutes.
Okay, Chapter 8 gave us a deeper dive into the three key components of Bayes' theorem. Where does Kurt go from there?
In Chapter 9, Bayesian priors and working with probability distributions, we really start to grapple with the subjectivity of prior beliefs
Okay.
and how they can influence our Bayesian analyses.
Okay, so we're tackling that controversy head on.
Exactly. And Kurt provides guidance on how to choose prior probabilities in a thoughtful and transparent way. He emphasizes that the choice of prior should be based on the best available information, whether that comes from previous research, expert knowledge,
Okay.
or even our own informed intuition.
So it's not about just picking a number randomly. It's about justifying our choices
Exactly.
and being clear about how our prior beliefs are shaping our analysis.
He also delves into how to represent those prior beliefs using probability distributions.
Okay, so instead of just saying, I believe there's a 50% chance of this happening, we can use a probability distribution to show the range of possibilities we consider plausible.
Exactly. And this approach allows us to express our uncertainty more accurately and to incorporate a spectrum of possible values into our calculations.
Can you give us an example of how this works?
Sure. Kurt uses a fun example from Star Wars,
Okay.
estimating the probability of Han Solo surviving the asteroid field in The Empire Strikes Back.
Okay, now that's an example I can get behind.
Right.
So our prior belief about Han's chances of survival might be based on what we know about his piloting skills, the dangers of asteroid fields,
Yeah.
and maybe even a bit of gut feeling.
Exactly. And instead of just assigning a single probability to his survival, like 70%,
Right.
we can use a probability distribution to represent a range of possibilities.
So we might say there's a 60% chance he survives,
Yeah.
a 20% chance he gets injured, and a 20% chance he doesn't make it. We're acknowledging that there's a whole spectrum of possible outcomes,
Right.
not just one definitive answer.
Precisely. And this approach gives us a more nuanced and realistic picture of the situation.
Okay, so we're using probability distributions to represent prior beliefs. What else does Kurt cover in this chapter?
He discusses the idea of weak versus strong priors.
Okay.
A strong prior means we have a lot of confidence in our initial belief, while a weak prior means we're more uncertain
Okay.
and open to being swayed by the data.
So choosing a strong prior is like saying, I'm pretty sure I know what's going on here.
Right.
While choosing a weak prior is like saying, I'm not really sure, so let's see what the data tells us.
Exactly. And Kurt explains that the best choice of prior depends on the specific situation. If we have a lot of relevant information, a strong prior can be useful. But if we're dealing with a lot of uncertainty, a weak prior might be a safer bet.
Okay, so it's about finding the right balance between our existing beliefs and our willingness to be influenced by new information.
Precisely. And this highlights the iterative nature of Bayesian analysis. We start with prior beliefs. We gather evidence.
Right.
We update our beliefs. And the process continues as we learn more.
Okay. Chapter 9 gave us a deeper dive into the world of prior beliefs and how to handle them responsibly. What comes next?
Chapter 10, Introduction to Averaging and Parameter Estimation, shifts our focus from beliefs to estimation.
So instead of just updating what we believe,
Right.
we're trying to figure out the actual values of things.
Exactly. And Kurt starts with the familiar concept of averaging, which might seem pretty basic at first glance.
Right. Everyone knows how to calculate an average. What's so special about averaging in the context of Bayesian statistics?
Kurt shows us that averaging is more than just a simple arithmetic operation. It's a powerful tool for minimizing error and getting closer to the truth.
Okay, I'm intrigued. Can you give us an example of how averaging helps us get closer to the truth?
Sure. He uses the example of estimating snowfall.
Okay.
Imagine you take measurements of the snow depth in different parts of your yard.
Okay, so I'm out there with my ruler,
Right.
diligently measuring the snow in various spots.
Exactly. But those measurements are likely to vary. Some spots might have deeper drifts due to wind, while others might have less snow because of trees or other obstacles.
Right, so I'm getting a range of values, not one perfect measurement of the true snowfall.
Precisely. And Kurt explains that by averaging those measurements, we're essentially canceling out those random variations.
So the high measurements and the low measurements balance each other out.
Yeah.
And we end up with an estimate that's closer to the average snowfall across the entire yard.
Exactly. And this concept of error cancellation through averaging is a fundamental principle in statistics, especially when we're trying to estimate unknown values based on multiple measurements.
Okay, so it's not just about getting the mean. It's about understanding how averaging helps us reduce the impact of random errors
Yeah,
and get a more accurate picture of reality.
precisely. And Kurt takes this concept a step further by introducing the idea of weighted probabilities.
Weighted probabilities, what does that mean?
It means that instead of treating all measurements equally,
Right.
we can give more weight to certain measurements
Right.
based on how reliable or
Yeah.
informative we think they are.
So if I have one snowfall measurement from a super accurate high-tech weather station
Yeah.
and another measurement from just eyeballing it,
Mm-hmm.
I would give more weight to the measurement from the weather station.
Exactly. And Kurt shows us how to factor these weights into our calculations to get even more accurate estimates. It's like fine-tuning the averaging process
Okay.
to give more influence to the measurements we trust the most.
Okay, so we're not just blindly averaging everything together.
Yeah,
We're taking into account the quality of our data
right.
and adjusting our calculations accordingly.
Precisely.
Mm.
And this nuanced approach is crucial when we're dealing with real-world data, which is often messy and inconsistent.
Okay, so we've talked about averaging, error cancellation, and weighted probabilities. What's the key takeaway from Chapter 10?
The key takeaway is that averaging is a powerful tool for estimating unknown values, but it's important to use it thoughtfully by understanding how errors can cancel each other out
Right.
and how to incorporate weighted probabilities.
Yeah.
We can make our estimates more accurate and reliable.
So it's about using averaging strategically,
Exactly.
not just mechanically.
And this chapter lays the groundwork for more advanced parameter estimation techniques that we'll explore in the chapters ahead.
Okay, I'm excited to see where this leads. What's next?
Chapter 11, measuring the spread of our data, moves beyond just looking at the average
Okay.
and dives into how we can understand the variability or dispersion of our data.
Okay, so we're not just interested in the center. We're interested in the edges, the extremes and
Yeah,
outliers.
Precisely. And understanding how spread out our data is crucial for drawing meaningful conclusions and making accurate predictions.
But why is the spread so important? Can't we just rely on the average to tell us what we need to know?
The average gives us a sense of the typical value, but it doesn't tell the whole story.
Okay.
Imagine you're comparing the heights of two groups of people.
Okay.
They might have the same average height, but one group might have a much wider range of heights, from very short to very tall, while the other group is more tightly clustered around the average.
Okay, I see. The spread gives us additional information about the distribution of the data,
Right.
not just the central tendency.
Exactly. And Kurt introduces several measures of spread that help us quantify this variability. I mean, absolute deviation variance
Okay.
and standard deviation.
Okay, let's unpack those one by one.
Yeah.
What's mean absolute deviation?
It's essentially the average distance of each data point from the mean. Imagine you have a bunch of measurements scattered around the average.
Okay.
The mean absolute deviation tells you, on average, how far each measurement is from the center.
So if the mean absolute deviation is small,
Yeah.
it means the data points are tightly clustered around the average. And if it's large, it means the data is more spread out.
Precisely. And it gives us a sense of how much variation there is in our data.
Okay, that makes sense.
Oh, what about variance? Variance is similar to mean absolute deviation,
Okay.
but it involves squaring the differences between each data point and the mean before averaging them.
Why do we square the differences?
Squaring has a couple of advantages.
Right.
First, it makes all the differences positive, which
Right.
simplifies the calculations.
Okay.
Second, it amplifies the impact of larger deviations, meaning those outliers have a bigger influence on the variance.
So it's like saying those extreme values that are far from the mean are really important for understanding the overall spread.
Exactly.
Yeah.
And this emphasis on outliers can be beneficial
Okay.
because it gives us a better sense of the full range of variability in our data.
Okay, so variance emphasizes the extremes. What about standard deviation?
Standard deviation is simply the square root of the variance.
Why take the square root?
Taking the square root brings the variance back to the same units as the original data, making it easier to interpret.
So if my data is measured in centimeters, the standard deviation will also be in centimeters.
Exactly. And the standard deviation is a really useful measure because it tells us the typical distance of a data point from the mean.
So a large standard deviation means the data is more spread out.
Right.
And a small standard deviation means it's more tightly clustered around the mean.
Precisely. And these measures of spread play a crucial role in many statistical analyses,
Okay.
including hypothesis testing and creating confidence intervals.
Okay, so Chapter 11 was all about understanding the importance of spread and those different measures of spread.
Yeah.
Absolute deviation
Yeah,
variance
right.
and standard deviation.
Right.
What's next?
Chapter 12 introduces one of the most important concepts in statistics, the normal distribution.
Yeah.
It's also known as the Gaussian distribution or the bell curve, and
Okay.
it pops up everywhere.
Okay, I've definitely heard of the bell curve before. Why is this distribution so special?
It's special for a few reasons. First, it's incredibly common in nature.
Okay.
Many natural phenomena like heights, weights, and IQ scores tend to follow a normal distribution. It's like the universe's default setting for how things are distributed.
So it's not just a theoretical concept that actually reflects how things work in the real world.
Exactly. And the normal distribution has some really convenient mathematical properties that make it easy to work with. It's like the math gods smiled upon statisticians when they discovered this distribution.
Okay, so it's common and mathematically convenient. Anything else that makes it stand out?
It forms the basis for a ton of other statistical techniques, like hypothesis testing, creating confidence intervals,
Okay.
and regression analysis. So understanding the normal distribution is like unlocking a whole new level of statistical power.
Okay, I'm ready to unlock that power. What are the key characteristics of the normal distribution that make it so useful?
First, it's perfectly symmetrical,
Okay.
meaning it's shaped like a bell curve with the highest point at the center,
Uh-huh.
which represents the mean, median, and mode all in one.
So it's balanced, with the most likely values clustered around the middle
Yeah,
and the less likely values tailing off on either side.
exactly. And its shape and characteristics are completely defined by just two parameters.
Okay.
The mean and the standard deviation. The mean tells us the center of the distribution, and the standard deviation tells us how spread out it is.
So if I know the mean and standard deviation of a normal distribution,
Yeah,
I can picture it in my head and know exactly what it looks like.
precisely. And knowing those two parameters allows us to calculate all sorts of probabilities associated with the distribution.
Like the probability of finding someone taller than 6 feet, if we're talking about heights.
Exactly. Kurt walks through the steps of calculating these probabilities using the normal distribution, which can be incredibly useful for all sorts of real-world applications.
Okay, so the normal distribution is symmetrical, defined by the mean and standard deviation,
Right.
and we can use it to calculate probabilities.
Mm-hmm.
What's the big takeaway from Chapter 12?
The takeaway is that the normal distribution is a fundamental building block in statistics. It's common, convenient, and the basis for a ton of other statistical techniques. Understanding the normal distribution is essential for anyone who wants to delve deeper into the world of data and statistics.
Okay, I'm adding master the normal distribution to my to-do list. What's next?
Chapter 13 introduces some essential mathematical tools for working with probability distributions and estimating parameters.
Okay.
The PDF, the CDF, and the quantile function.
Okay, so we're getting into the more technical side of things.
We are, but don't worry, Kurt does a great job of demystifying these concepts. Okay.
And showing how they work in practice.
Okay, good to know. Let's start with the PDF. What's that all about?
PDF stands for probability density function. It's a mathematical function that describes the probability of observing different values of a variable. It's basically a blueprint for how the probabilities are spread out across a range of possibilities.
So for our height example,
Yeah.
the PDF of the normal distribution would tell us the probability of observing different heights.
Exactly. It would show that heights closer to the mean are more likely, while heights further away from the mean are less likely.
Okay, that makes sense. What about the CDF?
CDF stands for cumulative distribution function.
Okay.
It's like a running total of the probabilities from the PDF.
So instead of giving us the probability of a single value,
Right.
it gives us the probability of getting a value less than or equal to a certain point.
Exactly. So if we're talking about heights,
Yeah.
the CDF would tell us the probability of finding someone shorter than, say, 6 feet. Okay, so it's like asking, what are the chances of someone being this height or shorter?
Precisely. And both the PDF and the CDF can be represented visually as curves,
Go ahead.
which can make them easier to understand.
Okay, I'm starting to get a picture of how these work. What about the quantile function?
The quantile function is basically the inverse of the CDF.
Okay.
It tells us the value that corresponds to a given probability.
So instead of giving it a value and getting a probability,
Right.
we give it a probability and get a value.
Exactly. For example, If we give the quantile function for the normal distribution a probability of 0.5, it will tell us the median height, which is the height that splits the distribution in half.
Okay, so it's like asking what height is taller than 50% of the population.
Precisely. And the quantile function is useful for calculating things like percentiles and confidence intervals,
Right.
which we'll get into later.
Okay, so we've got the PDF, which shows us how probabilities are distributed.
Yeah.
The CDF, which gives us cumulative probabilities. And the quantile function, which works in reverse. What's the big takeaway from Chapter 13?
The key takeaway is that these three mathematical tools are essential for working with probability distributions, understanding how data is spread out,
Okay.
and making informed inferences about populations based on samples.
So they're like essential tools in our statistical toolkit for analyzing data and making sense of uncertainty.
Exactly. And we'll see how they're used in more detail as we continue our exploration.
Okay, I'm ready for more tools. What's next?
Chapter 14, Parameter Estimation with Prior Probabilities, takes us back to the Bayesian approach
Okay.
and shows us how to incorporate our prior beliefs into the process of estimating unknown values.
Okay, so we're bringing those prior beliefs back into the picture.
Exactly. And this is one of the key differences between classical statistics and Bayesian statistics. Classical statistics generally focuses on estimating parameters solely based on the observed data,
Okay.
while Bayesian statistics allows us to incorporate our prior beliefs as well.
So it's like saying, we don't start with a blank slate. We bring our existing knowledge and beliefs to the table.
Precisely. And this can be especially valuable when we have limited data. The prior beliefs can help us to stabilize our estimates and prevent us from jumping to conclusions based on a small sample size.
Can you give an example of how this works in practice?
Sure. Kurt revisits the example of estimating a website's conversion rate, the percentage of visitors who sign up for something like an email list or a free trial.
Okay, so if we're launching a new website or campaign,
Yeah,
we might want to estimate how well it's going to convert visitors into customers.
exactly. And in classical statistics, we just use the observed data,
Right.
get the number of visitors and the number of signups
Yeah.
to estimate this conversion rate. But in Bayesian statistics, we can factor in our prior beliefs about how well we think the website should perform.
So if we have reason to believe the conversion rate should be around 5% based on industry averages or past experience,
Right.
we can incorporate that into our estimation.
Precisely. We can represent that prior belief using a probability distribution,
So,
like the beta distribution we talked about earlier.
and how do we combine that prior belief with the actual data we collect?
We use Bayes' theorem, of course.
Okay.
We calculate the likelihood of the observed data given different values of the conversion rate, and then combine that likelihood with our prior distribution to come up with a posterior distribution for the conversion rate.
So the posterior distribution reflects both the data we've collected and our prior beliefs about the conversion rate.
Exactly. And as we collect more data, the influence of our prior belief gradually diminishes, and the data starts to speak for itself.
Okay, that makes sense. So we're using Bayes' theorem to blend our subjective beliefs with the objective evidence from the data to arrive at a more informed estimate.
Precisely. And Kurt emphasizes that the choice of prior is important.
Yeah.
We need to choose priors that are both justifiable and transparent.
So we shouldn't just pick a prior that gives us the answer we want.
Right.
We need to think critically about what we know and what we don't know.
Exactly. And Kurt provides guidance on how to select priors,
Okay.
including the use of non-informative priors when we have very little or no prior information.
Okay, so we're learning to be responsible Bayesians, carefully considering our priors and how they influence our estimates. What's the key takeaway from Chapter 14?
The key takeaway is that Bayesian parameter estimation allows us to bring our prior beliefs into the analysis, which can be particularly valuable when we're dealing with limited data or trying to leverage expert knowledge.
So it's about finding that sweet spot between what we believe and what the data tells us.
Exactly. And this Bayesian approach is becoming increasingly popular in fields like finance, medicine, and machine learning, where researchers often need to make decisions based on incomplete information.
Okay, Chapter 14 gave us a deeper dive into Bayesian parameter estimation. What's next on our agenda?
Chapter 15, From Parameter Estimation to Hypothesis Testing, marks a shift from estimating unknown values to testing specific claims or hypotheses about the world.
So instead of just asking, what's the value of this thing?
Right.
We're asking, is this claim true or false?
Exactly. And Kurt uses a real-world example to illustrate this concept.
Okay.
A/B testing, which is widely used in marketing and product development.
Okay, so we're getting into practical applications here.
Yeah.
What's A/B testing all about?
It's basically a way of comparing two versions of something to see which one performs better.
Right.
For example, if you're testing a new website design,
Uh-huh.
you might show version A to half your visitors and
Right.
version B to the other half, then see which version leads to more conversions, more people buying something,
Yeah.
signing up for a newsletter,
Yeah,
or
right.
whatever your goal is.
Right. So it's like a head-to-head competition between two versions of a product or design.
Exactly. And Kurt explains how to design and analyze A/B tests using Bayesian methods.
How does the Bayesian approach differ from the traditional way of doing A/B testing?
Traditional A/B testing often relies on p-values
Uh-huh.
and the concept of statistical significance to make decisions.
Okay.
The Bayesian approach, on the other hand, focuses on calculating posterior probabilities
Right.
and comparing the evidence in favor of each hypothesis.
So instead of just looking at p-values,
Yeah.
we're looking at the weight of evidence supporting each version.
Precisely. And Kurt shows us how to do this using the Bayes factor,
Mhm.
which we talked about earlier.
Right.
It tells us how much more likely the data is under one hypothesis
Okay.
compared to another.
So instead of just saying, this version seems better,
Yeah.
we can actually quantify how much stronger the evidence is for one version over the other.
Exactly. And this can lead to more informed and nuanced decisions,
Mhm.
especially when we're dealing with complex scenarios.
Okay, so we're using the Bayes factor to weigh the evidence in A/B testing. What else does Kurt cover in this chapter?
He walks us through the process of building a Bayesian A/B test,
Okay.
from setting up the hypotheses to collecting data to analyzing the results. He also discusses important considerations like sample size
Uh-huh.
and how to determine how many participants we need for a reliable test.
So he's giving us a practical roadmap for conducting Bayesian A/B tests in the real world.
Exactly. And he argues that the Bayesian approach can be more intuitive and informative than traditional methods because it allows us to update our beliefs about the relative performance of each version as we collect more data.
So it's not just a static analysis. It's a dynamic process
Yeah.
that allows us to refine our understanding as we learn more.
Precisely. And this dynamic approach is particularly well suited to the fast-paced world of online marketing and product development,
Yeah.
where decisions often need to be made quickly and adapted based on new information.
Okay, so chapter 15 was all about Bayesian A/B testing and how we can use it to make data-driven decisions. What's next?
Chapter 16 delves deeper into the concept of the Bayes factor. Okay.
And introduces a related concept called posterior odds. It's called Introduction to the Bayes Factor and Posterior Odds, the competition of ideas.
Okay, so we're getting into the nitty-gritty of how we compare different hypotheses
Right.
and weigh the evidence.
Exactly. And the Bayes factor, as we've discussed, is a key tool for quantifying the strength of evidence in favor of one hypothesis over another.
Right, so instead of just saying, this hypothesis seems more likely, we can actually assign a number to that likelihood ratio.
Precisely. And that number tells us how much more likely the observed data is under one hypothesis compared to the other.
Can you give an example of how this works in practice?
Sure. Kurt uses a scenario from medicine,
Okay.
trying to determine if someone has a rare disease based on their symptoms. Let's say someone is experiencing fatigue, muscle weakness, and joint pain.
Okay, so our hypotheses are this person has the rare disease versus this person doesn't have the rare disease.
Exactly. Now, we need to consider how likely those symptoms are under each hypothesis.
If the rare disease is known to cause those symptoms in a high percentage of cases, the likelihood of seeing those symptoms if the person has the disease would be high.
Right. So the symptoms are a good indicator of the disease.
Exactly. But we also need to consider how common those symptoms are in the general population. If those symptoms are fairly common, even without the rare disease,
Okay.
then the likelihood of seeing those symptoms, even if the person doesn't have the disease, might also be relatively high.
Okay, so we have to consider how specific the symptoms are to the disease.
Right.
If they're common even without the disease, they're not as informative.
That's right. And that's where the Bayes factor comes in.
Okay.
It's the ratio of those two likelihoods. The likelihood of the symptoms given the disease divided by the likelihood of the symptoms given no disease.
So if the symptoms are 10 times more likely if the person has the disease compared to if they don't, the Bayes factor would be 10.
Exactly. And a Bayes factor of 10 means the data, in this case, the symptoms, is 10 times more likely under the disease hypothesis than under the no disease hypothesis.
Okay, that makes sense.
Yeah.
So how does the concept of posterior odds fit into this?
Posterior odds represent the odds of one hypothesis being true compared to the other after we've considered the evidence.
Yeah.
It's basically our updated belief about the relative likelihood of the two hypotheses.
So it's like the final score after we've weighed the evidence.
Exactly.
Yeah.
And the way we calculate posterior odds
Okay.
is by multiplying our prior odds by the Bayes factor.
Higher odds. What are those?
Prior odds represent our initial belief about the relative likelihood of the two hypotheses before we see any evidence.
Okay.
So if we think the disease hypothesis is twice as likely as the no disease hypothesis based on things like the person's age,
Yeah.
family history, or
Yeah.
other risk factors,
Okay.
our prior odds would be 2 to 1.
Okay, so the prior odds reflect our initial hunch about which hypothesis is more likely.
Exactly. And then we use the Bayes factor to adjust those odds based on the evidence we've observed.
So if our prior odds were 2 to 1 and the Bayes factor is 10, meaning the data is 10 times more likely under the disease hypothesis,
Right.
our posterior odds would be 20 to 1.
Precisely. And that would mean that after considering the evidence,
Yeah.
the disease hypothesis is now considered 20 times more likely than the no disease hypothesis.
Okay, I see how the Bayes factor acts as a multiplier,
Yeah,
amplifying or diminishing our initial beliefs based on the strength of the evidence.
exactly. And this quantitative approach to weighing evidence is incredibly valuable,
Huh.
especially in fields like science and medicine,
Right.
where decisions can have real-world consequences.
Okay, so Chapter 16 gave us a deeper understanding of the Bayes factor
Yeah.
and how it helps us compare hypotheses and update our beliefs based on evidence. What comes next?
Chapter 17 takes a fun detour into the world of science fiction, using an episode of The Twilight Zone to illustrate the principles of Bayesian reasoning and the power of prior beliefs.
Okay, so we're taking a break from formulas and equations
Yeah,
to explore Bayesian thinking through storytelling.
exactly. And it's a great way to see how these concepts play out in a different context.
Okay.
The episode Kurt uses is called Nick of Time,
Uh-huh.
and it features a couple who are stranded in a small town
Okay.
and come across a fortune-telling machine called the Mystic Seer.
A fortune-telling machine. Sounds a little spooky, even for the Twilight Zone.
Right. And the machine starts making predictions that actually come true,
Uh-huh.
leading one of the characters, Don, to
Yeah.
become convinced that it's genuinely supernatural. The other character, Pat, remains skeptical.
So they're both observing the same evidence,
Right.
the machine's accurate predictions,
Yeah,
but they're interpreting it very differently.
precisely. And Kurt points out that this difference in interpretation comes down to their different prior beliefs.
Uh-huh.
Don,
Who already believes in the supernatural has a higher prior probability for the hypothesis that the machine is real.
okay.
Pat,
Alright.
who's more skeptical,
Yeah.
has a lower prior probability for that hypothesis.
So their prior beliefs act like a lens, coloring how they see the evidence.
Exactly.
Yeah.
And Kurt uses this example to illustrate how powerful prior beliefs can be.
Mm-hmm.
They can shape our perceptions and influence how we interpret even the most compelling evidence.
Okay, so it's a reminder that we all bring our own baggage to the table when we're evaluating evidence,
Right.
and we need to be aware of that.
Precisely. And Kurt emphasizes that being aware of our prior beliefs is crucial for critical thinking
Mm-hmm.
and rational decision-making.
Yeah.
We need to be willing to challenge our assumptions and consider alternative explanations for the things we observe.
Okay, so The Twilight Zone has given us a fun and thought-provoking example of how Bayesian reasoning plays out in a different context.
Yeah.
What else does Kurt explore in this chapter?
He revisits the Bayes factor.
And shows how it can help us to quantify the strength of evidence in favor of one hypothesis over another, even when dealing with seemingly subjective beliefs.
So we can actually measure how much the evidence supports Don's belief in the fortune-telling machine versus Pat's skepticism.
Exactly. And that's the beauty of the Bayes factor. It helps us bring some objectivity into situations that might seem entirely subjective.
Okay, so Chapter 17 was all about the power of prior beliefs and how the Bayes factor can help us quantify the evidence. What comes next?
Chapter 18, When Data Doesn't Convince You, tackles the intriguing situation where people hold on to their beliefs even when the evidence seems to contradict them.
Okay, so we're talking about those times when no amount of data can change someone's mind.
It can be frustrating, but it's a common phenomenon. And Kurt explores the reasons why people might cling to their beliefs even when the evidence seems overwhelming.
So it's not always about stubbornness or closed-mindedness.
Right.
Sometimes it's about deeply held convictions,
Yeah.
emotional attachments, or even a lack of understanding of the evidence itself.
Exactly. And Kurt uses the example of a friend who claims to have psychic powers. Imagine this friend makes a series of predictions,
Okay.
and some of them actually come true.
Okay, so we're seeing some evidence that supports their claim,
Yeah.
but we're still not convinced.
Right. And Kurt explains that our prior belief about psychic powers might be so strong, either for or against, that even a string of successful predictions won't sway us.
So if our prior probability for psychic powers exist is extremely low,
Yeah,
even a mountain of evidence might not be enough to budge it.
precisely. And in these cases, bombarding someone with more data might not be the most effective strategy. Instead, Kurt suggests focusing on understanding their prior beliefs and why they hold them so strongly.
So it's about having a conversation, not a confrontation.
Right.
Trying to understand where they're coming from rather than just trying to prove them wrong.
Exactly. And that approach can be more effective in bridging the gap between beliefs and evidence.
Okay, so we've talked about the persistence of belief, even in the face of contradictory evidence. What else does Kurt explore in this chapter?
He emphasizes the importance of considering alternative explanations. Instead of just focusing on one possible explanation, we should generate multiple hypotheses and see how well each one fits the data.
So in the psychic friend example,
Yeah.
instead of just focusing on psychic powers,
Right.
we might also consider explanations like lucky guesses,
Yeah.
coincidences,
Yeah.
or even clever tricks.
Exactly. And by comparing the likelihood of the data under each hypothesis, we can get a better sense of which explanation is most plausible.
So it's like expanding our view beyond a single tunnel vision explanation
Right.
and considering a wider range of possibilities.
Precisely. This approach helps us avoid confirmation bias,
Mm-hmm.
which is the tendency to favor evidence that supports our existing beliefs
Yeah.
while downplaying evidence that contradicts them.
Okay, so Chapter 18 was a reminder to be open-minded,
Yeah.
consider multiple explanations, and avoid cherry-picking evidence to fit our preconceived notions. What comes next?
Chapter 19, From Hypothesis Testing to Parameter Estimation, brings us full circle,
Okay,
connecting those two key concepts that we've been exploring throughout the book.
so we're bridging the gap between testing claims
Right.
and estimating unknown values.
Exactly. And Kurt explains that these two processes are intertwined.
Mm-hmm.
Often we're not just interested in whether a hypothesis is true or false. We also want to know the magnitude of the effect,
Right.
the size of the difference,
Yeah.
or the value of some parameter associated with that hypothesis.
So if our hypothesis is that a new drug is effective in treating a disease, we might also want to know how effective it is,
Yeah,
how much it reduces symptoms or improves outcomes.
precisely. And Kurt explains how Bayesian methods allow us to do both test the hypothesis and estimate the parameter simultaneously.
Okay, so we're getting more bang for our buck with our statistical analysis.
Exactly. It's a more efficient and holistic approach. To illustrate this, he uses the example of a carnival game where you're trying to win a prize by throwing darts at a target.
Okay, I can picture it. The barker is promising amazing prizes, but the game seems a little too hard to win.
Right. So our hypothesis might be that the game is rigged.
Mhm.
The probability of winning is actually lower than the barker claims.
Exactly. And we can use Bayesian methods to both test that hypothesis and estimate the true probability of winning.
Precisely. So we're simultaneously evaluating the fairness of the game
Right.
and figuring out what our actual chances of winning are.
Exactly. Kurt explains that we can do this by considering a range of possible probabilities for winning and then calculating how likely the observed data is the number of wins and losses
Right.
under each probability.
So we're testing out different possibilities and seeing which one best fits the data.
Yeah.
And then we use Bayes' theorem to combine those likelihoods with our prior beliefs.
Okay.
Maybe we're naturally skeptical of carnival games.
Right.
To arrive at a posterior distribution for the probability of winning.
And that posterior distribution gives us both an estimate of the true probability of winning
Yeah.
and a sense of how certain we are about that estimate.
Precisely. It's a much more nuanced and informative approach than just conducting a hypothesis test or estimating a parameter in isolation.
Okay. Chapter 19 showed us how to connect hypothesis testing and parameter estimation using Bayesian methods. What's the final takeaway from our deep dive into Bayesian statistics the fun way?
Well, I hope you've come away from this with a sense of how powerful and versatile Bayesian statistics can be. It's not just about crunching numbers. It's about thinking critically,
Yeah.
updating our beliefs in light of new evidence,
Right.
and making more informed decisions in a world full of uncertainty.
It's like a mental upgrade for navigating the complexities of the world.
Exactly. And while the math can seem intimidating at times,
Uh-huh.
Wolkert does a fantastic job of demystifying it and making it accessible to anyone who's willing to put in a little effort.
He really does make it fun. So what are some key takeaways you'd like our listeners to remember as they continue their own explorations of Bayesian thinking?
First, embrace the idea that probability is a way of quantifying uncertainty. It's not about predicting the future with certainty. It's about understanding the likelihood of different outcomes
Yeah.
and making decisions based on those probabilities.
So instead of black and white thinking,
Right.
we're embracing shades of gray,
Yeah,
acknowledging that we can't always know things for sure.
exactly. Second, remember that our prior beliefs matter. They influence how we interpret evidence and make decisions.
Uh-huh.
The key is to choose those priors thoughtfully and transparently, justifying our choices based on the best available information.
So we're not just pulling beliefs out of thin air, we're grounding them in evidence and logic.
Precisely. And third, always be open to updating your beliefs as you gather new evidence.
Okay.
The world is constantly changing, and our understanding of it should evolve as well. That's the essence of Bayesian thinking, a dynamic, iterative process of learning and refining our beliefs.
It's like a continuous feedback loop between our beliefs and the evidence we encounter,
Yeah,
shaping and reshaping our understanding of the world.
exactly. And I think that's a powerful and empowering way to approach life in general. So, to our listeners, I encourage you to keep exploring, keep questioning,
Yeah.
and keep learning. The world of Bayesian statistics is vast and fascinating,
Right.
and it has the potential to transform the way you think and make decisions.
I couldn't agree more. Thanks for joining us on this deep dive into Bayesian statistics the fun way.
Yeah,
We hope you've enjoyed the journey.
it's been my pleasure.